For a while, let's just forget about the truthful revelation. We have discussed about this dominant strategy implementability and Bayesian implementability. For a while, let's just keep them aside and ask the following question, that how difficult is aggregating opinions in general? So for instance, can we actually create meaningful social preference orders from individual preferences? That is going to be the point of discussion in this module and in the subsequent modules. So in this context, so why are we doing this? Because we want to see that there are some difficulties in aggregating opinions even without truthful revelation. And we'll see some of the landmark results of social choice theory, namely the arrows result. So let us look at this particular setup. So this is named after Arrows, Kenneth Joseph Arrow, who is one of the founders of this social welfare theory. So this setup is known as this Arrow's social welfare function setup. So let us assume that we have a finite set of alternatives given by this set A, and we have a finite set of players as usual, and every player I has a preference order which will be denoting by Ri. So this is a binary relation over this set A. So there are different other ways of representing this. So in some books you will find this kind of a notation to denote that this is a preference ordering, but for simplicity we are going to use this R of I. So the meaning of when we write A Ri of B is that A is at least as good as B. So it may be the case that A is strictly above A, B, C, or maybe A and B are at the same preference order and C and D are in other places. So both these two cases can be represented by A is at least as good as B. Right? Now, because this is a relation, there are certain properties that we will be assuming for this relation. The first property that we'll assume is called completeness. That means that for every pair of alternatives in this set A, pick any two alternatives A comma B, either A will be weakly preferred than B, or B will be weakly preferred than A, or it may be both. Right? So, but at least one of them should happen. So it can never happen that there exist two alternatives which are not related in any way. So you cannot really have any preference relation between them. The second property is that of reflexivity. If A belongs to A, capital A, then A must be at least as much as preferred as A itself. And the third property is transitivity. That is, if you prefer A at least as much as B, and B at least as much as C, then you must be preferring A at least as much as C for all A, B, C that is belonging to A, and for every player I in N. Now, these are the three fundamental properties of Ri that we are going to assume throughout. Now, for the notation, we will denote all the set of preference orderings of all the players to be equal to script of R. So also at some point we will also use this ordering which are linear ordering. So you can think of this as strict preferences. There are no indifferences in this preference. How can we state that formally? If you have any A and B, any pair of alternatives A and B, and if this happens that A is at least as much preferred as B, and B is also at least as much preferred as A, then it must be the case A and B are the same. So they must not be two different alternatives. In other words, this is actually ruling out the possibility of any indifferences. You can always have preferences like A, B, C which are strict, but you can never have A and B comma C, because in B comma C you have the same preference ordering. B is at least as much preferred as C, and C is also at least as much preferred as B. We are ruling out those possibilities. So those kind of orderings are called linear orderings or strict preferences. And similarly, we are going to denote the set of all linear orderings with script of P. In a very similar way, if we have any arbitrary ordering R of I, this can be decomposed. Ri is a weak preference ordering, and this can be decomposed into two parts. One is the asymmetric part, where you have strict preferences, and the symmetric part, where you have weak preferences. So they are equivalent in some sense. So let us look at this example. So suppose Ri is this. So you have A, the most preferred alternative, then B and C are at the same level. You prefer them equally, and D is the worst. You don't prefer it at all. Then if you want to write this down in the formal way of defining relations, remember that relations are nothing but subsets of the Cartesian product of A comma A. So this relation Ri is nothing but a subset of this A cross A, right? So we can write this as this tuples. So this relation, you can write this relation in the following way. So A is preferred then over B, A is preferred over C. Then you have these two things, B is preferred over C, and also C is preferred over B. And then you have B is preferred over D, C is preferred over D. So this 6 tuples together completely represent what we have written here. Now by this asymmetric and symmetric part of Ri, what we denote is that you figure out what is the linear part in this. So ABD is a linear part, ACD is linear part. So only these things which are shown in red are the linear part, representing the linear part in this relation Ri. So that we are going to call as the asymmetric part. The symmetric part is where you have B comma C as well as C comma B, right? So this is the indifferent part of player I, right? That is denoted by I of I. So any arbitrary ordering can be decomposed into this asymmetric and symmetric parts. Now, what is an Aerovian social welfare function? We use the acronym ASWF. So this is a mapping when you have every player has a preference ordering, as we have defined before. This function takes all those orderings and gives a social ordering, a collective ordering. So you can imagine that you have this individual RIs, R1 to Rn. These are the preference ordering over the same set A for each of these individuals. F is this function which takes them as input and pops out one social ordering. So this is also an ordering over all these sets. And to distinguish between the asymmetric part, so like every R has a asymmetric and symmetric part, therefore the collective outcome, the social ordering, will also have a asymmetric and symmetric part. By hat we are going to denote the asymmetric part of it, and by a bar we are going to denote the symmetric part of f of r. So with that, we can now define two very important properties which will be required to present the main result of this module. So this is known as the weak Pareto, or sometimes we will just use WP for short. So this says that a social welfare, Aerovian social welfare function f satisfies this property if for every a comma b that lives in this set A, we know this the meaning of this notation, that whenever A is strictly preferred over B for all these players. So you can imagine that I don't really care about the positions of the other alternatives, but A is above B, right? So for all the players A is above B, then it must be the case that when you have this collection and apply F on it, the final outcome should also have A over B. So this is called weak Pareto. But look at the requirement. This requires A to be strictly above B. So this relationship is the linear order here, right? So that is a little strict requirement. Now you can equivalently define something called a strong Pareto, SP for short. So what does this mean? So the strong Pareto notion actually makes this if condition a little weaker. So what does it say is that you can have A above B, or at least as much as B. So both these two things are okay. So A can be, so in some other preferences maybe A is much above B, So this equivalence is also okay. So it can be weakly as much preferred as B for all the players, but there must exist some player for which this preference is strict. So that is what is meant by this one. And if that happens, then this property strong Pareto guarantees that your final outcome should be such that A is strictly preferred over B. So that should be the property of the social ordering. Now you can actually think for a while, pause this video and think about which property implies the other. So between strong Pareto and weak Pareto, which one implies which one? So if you think carefully, you can see that here the if condition is a little weaker. So you are actually trying to satisfy the same conclusion with a weaker if condition. So therefore this the property strong Pareto is stronger or more restrictive than the weak Pareto requirement, because there the if condition is more strict than the if condition of strong Pareto, and the conclusion is the same. So if you want to prove it directly, so you can see that you are given, so the final conclusion here is that strong Pareto implies weak Pareto. Why? So you are given this property here. Now you will have to prove that this holds. So again, for weak Pareto, you can assume that this if condition holds. You'll have to show that if this holds, then this should hold. And you also have at your disposal the property of strong Pareto. You know that this social welfare function f satisfies strong Pareto. Now what is the if condition? That A is strictly above B for all the players. Well, this definitely satisfies the if condition of the strong Pareto condition. I mean, it just says that A has to be at least as much as B, and there must be at least one player for which it is strict. But in the if condition of weak Pareto, all these conditions, the preferences over A and B is strict. And if that happens, of course, by strong Pareto, we can say that this inequality holds. So if a social choice function, social welfare function satisfies strong Pareto, then it must satisfy weak Pareto. Therefore, strong Pareto implies weak Pareto. Think about this for a while, and the meaning of this notation and also this implication will be very obvious to you. Now let us look at the following definition of agreement. So let us consider two preferences of player I. One is Ri and the other one is Ri prime. We say that these preferences of player I agree on these two alternatives A, B for agent I if the following things happen: that whenever A is strictly preferred over B, A is strictly preferred over B even in the P prime. So in one of these preference profiles, A is strictly above B. Here also it should be strictly above B, and vice versa. If B is strictly above A, and then it should imply that B is strictly over A even in the other preference profile, and vice versa. And if A and B are indifferent, I mean if in Ri they are at the same level, then they must also be at the same level in Ri prime. So then we will say that these two things agree. So in some sense you can think of A and B. So whenever A is above B in Ri, there A is still above B. I don't really care about the positions of the other alternatives. So there might be some other C here, D here, and in this case maybe C, D, and E are in between them. But all that we care about is that they agree on the relative positions of A and B. Right? That is all that we care about. This is what is meant by the agreement of two preference profiles over a pair of alternatives. So we'll usually denote this with this following shorthand, that we restrict this Ri only between A and B, and that is the same as the restriction of Ri prime between A and B, right? And when this holds, if this agreement holds for every agent, then we'll just write R restricted to AB is equal to the R prime restricted to AB. Right? So that is the agreement of the whole preference profile. What it means is that A is, let's say, above B, and for player 1, let's say, and for player 2 maybe B is above A, and for player 3 maybe A and B are at the same position. Then I don't really care about the other position. So this is, if this is R, in R prime what should happen is that A should still be above B for player 1. For player 2, B should still be above A. The position of the other players, of the other alternatives might change, and A and B should be at the same position for the third player. So this should hold. So this is the meaning of the agreement of two different preference profiles for a pair of alternatives. Now we come to a very important definition, which we call the independence of irrelevant alternatives. Independence of irrelevant alternatives, also written as IIA for short. So we say that a social choice function satisfies this property of IIA if you pick any pair of alternatives, A comma B in A, and whenever two different preference profiles, let's say R and R prime, they agree on these two alternatives A comma B, so the agreement that we have already defined before, it must be the case that the social ordering, that aggregated ordering, must also respect the same relative ordering. So they should also agree on these two alternatives A comma B. So think about this for a moment. We had the example of two things, R and R prime. So this property IIA is saying that if you have kept A above B when you have chosen this f of R, then you should continue to hold that same position in R prime as well. So if R should have A over B, and also similarly, so if you have done this, so if A was preferred to B in FR, then it must be the case that A must also be at least as good as B in R prime, in F of R prime, right? So this is meant by this independence of irrelevant alternatives. In other words, it is trying to say that because the relative position of A and B are the same in R and R prime, the irrelevant alternatives, the other alternatives, must not play a role in determining the relative position of A and B in the aggregated profile, in the aggregated preference. Let me show you with a little elaborate example. So suppose these are the two preference profiles R and R prime, and now let us consider two very natural things which will help us appreciating the point of IIA. So let us first consider what we will call as a scoring rule. So let's say we put some scores. So for each player, S1, S2 up to Sn, so here only 4 alternatives are there, 4 positions. So each of this, for every player, the alternative that is in the first position gets this score of S1, and similarly for others, and then finally you add the scores of the same alternative for different players. So in this case, for the score for A will be, so let's look at one specific scoring rule where the topmost one gets 1 and every other place gets 0. So this is known as the plurality score, as we have already mentioned here. So all the other positions are weighted 0 and only the topmost position is weighted 1. So in that case, the score R here, the score of R here is going to be 2 for A. So this score of 2 is for A. For B, it is 0. And for C and D gets 1. So this is for C and 1 for D. Right? So that is the total score for each of these. And here, so if you want to look at the final ranking, you can see the final. So according to the scoring rule, the final ranking of F of R, so F of let's say plurality of over R, should be the case where you have A on top because it has the highest score, C and D are at the same position, that is the second position, and B is at the bottommost, right? Similarly, if you do this for R prime, you can find that the f of plurality on R prime will be something like B will be on top because it has the highest score, and C and D again will be in the joint second position, and A will be at the bottom because A score there is 0. Now what you can notice here is that between A and B, the relative position, they do really agree on these two preference profiles R and R prime. So in other words, we can say that R given A comma B is actually equal to R prime given R A comma B. Why? Because A is above B here. So again, A is above B here. For the second player, A is above B again. So A is above B here also. For the third player, B is above A, and here also B is above A. And for the last player, it is above A, B is above A, and B is above A. So these two things agree when you restrict it to these two alternatives A and B. But whenever you are looking at the aggregated profile, you see that under plurality, A is above B here, while in R prime, B is above A here. Right, so that is actually violating the condition of independence of irrelevant alternatives. So plurality does not satisfy IIA, right? So the answer to this question is no. Now we look at another possible outcome rule, which is, let's say, dictatorship. So maybe you can just pick one player, let's say player 3 in this case, and you always output that player's preference profile as the outcome. Will IIA be satisfied? Of course, yes, because the point is, if it satisfies, so if it agrees, whenever this R and R prime agrees on a pair of alternatives, that must agree on the same player. So for player 2, if you look at B and A, of course B and A will be in the same order, because here also you are going to pick this as the outcome, the social outcome. Here also you are going to pick this as the outcome. Whatever is the order relative order between B and A will get satisfied in both these two cases. So quite trivial, even though this mechanism, this dictatorship is a very strange social welfare function that satisfies this IIA condition. Now, given that we understand the property of independence of irrelevant alternatives, now it is the right position to state the theorem, which is one of the very first theorems of social choice theory. This is due to Arrow, and it says that if you have at least 3 alternatives or more, then any Aerovian social welfare function f that satisfies these two properties, weak Pareto and this independence of irrelevant alternative, then it must be dictatorial. So this is the Arrow's characterization theorem only with these two properties. So note that here we are not talking about whether these types or their preference profiles are private or not, they are truthfully revealed or not. Even if you, as a mechanism designer, knew their preference profiles perfectly, it is very difficult to aggregate them into something reasonable. So something that satisfies weak Pareto and independent of irrelevant alternatives. Apart from dictatorship, there is no other mechanism which can do it.